So now I got the stream on. Alright, so it should appear in maybe another 10 seconds or so. There's a really horrible lag between OBS and YouTube Studio. So it's starting to do something. I can see it. Okay, it should be on right now. So there's a significant lag, and the timestamp is really good for checking that too, because you can see on YouTube versus on Discord, the time is quite different. Anyway, so let's go ahead and get started with question number 1. The question says the load LD instruction loads content from RAM to a register. The RAM location is specified by another register. The general format to use this mnemonic is LDX in parentheses Y. X refers to one of the 4 registers, A, B, C, or D, and same thing for Y. Note that X and Y, they can be the same register. Look at the opcode table and find out the actual binary code for the following mnemonic. So in this case, we have register C as in place of X, and then you have register D in place of Y. So I think most people got this one because I didn't have a lot of people asking about question number 1. So what we'll do is we are going to look up the LD instruction in the opcode table. And it is over here, row 23. So when we look at the LD instruction, we can see that 0111, which is a 7 in hexadecimal, is fixed. Okay, so that portion you cannot, there's nothing to calculate about that portion. And then we got XX and YY. So XX and YY depends on who is, which register is register X and which register is register Y. So getting back to the question, I think it's this one over here. So we have a 7, and then C is register C is 10 in binary, and then register D is 11 in binary. So the least significant 4 bits in binary is going to be 10 for the C and then 11 for the D, and in hexadecimal that is B, okay, because it's 11 in base 10, so it is a B in hexadecimal. So now the code should be 7F. And the answer should have exactly 8 bits, so we have to express it in binary, which is 0, 1, 1, 1, and then we have a 1, 0 for register C, and then a 1, 1 for register D. So are there any questions about number 1? Okay, questions about number 1. All right, so now we move on to question number 2, which is when, this is when people start to have questions. Is about number 2, and some people ask about, what it is asking, because, they maybe need some clarification of what is microcode and what is a slice and what does the word implement means. Alright, so let's read the question first. Now start up Logisim and load processor 0003.circ. In the ROM component, what is the address of the first microcode slice to implement the instruction that we just worked on, in the previous question? State your answer in hexadecimal digits without using the 0x prefix. Use all lowercase in the number because you can have A to F as digits in a hexadecimal number. All right, so let's find out what the question is really asking. So for one thing, we know it has to do with ROM component. So let me pull Logisim into view right here. All right, so we know it has to do with the ROM component, which is this guy over here. And the question is asking, so the key to understanding this particular question or what it is asking has to do with the other words. Okay, so what is a microcode slice? Okay, well, a microcode slice is really a location in the ROM. Okay, that's basically what it is, because a slice of microcode is what specifies all the bits that we need in order to configure the multiplexers, demultiplexers, configure the registers and also RAM so that they can get the job done. Okay, so we got some questions in Discord, and this is the part of the reason why I want to use an overlay, so that in OBS, we can actually see all the conversations in Discord. But I found that there's not enough space to do it, so that's why I turned off that particular plugin. All right, so let's answer or address Martin's comment first, and then Catherine is still typing. I was also confused by the terminology microcode slides and looked at the last lab and then rewatched the YouTube video to understand it. So I'm assuming it is understood, because during yesterday's demonstration, I kind of introduced the word slice and said that it is the same as a location in the ROM. I call it a slice because it's a slice of time. Okay, it is a slice of time in the execution of an instruction. And then Catherine says on each of these, it was a bit difficult to figure out when I needed to run the assembler in order to solve and when I could solve them on my own. Oh, okay. So the question or the comment is about how to solve the problem. So that's a very good question. And as I go through this, I will show you guys um, basically for each one, you probably can solve it, without using the assembler. You can solve it analytically, but the question is, there may be some knowledge that I have not yet introduced to solve it without the assembler. But in this case, you can use any tools to do it. Okay, so that's the whole point. Is given all the tools and given everything, all the documentation that you have, you can use any in any combination to solve the problem. So that might leave you still kind of not fully understanding something, but you can use any tools to solve the problem. You figure several can be done in either way, but it was confusing. Okay, so yes, so for all the labs, for the most part, you can use any tools, to solve the problems, and that's part of the problem-solving process. Is you just have to look at whatever tool is available in your tool set, and just utilize whatever works, at least at the time. Now, it doesn't mean that there's a little mysterious tool in your bag and it somehow fixes the problem, and you want to know more about how that tool works. That's perfectly okay. So we can address those in today's lecture. So let's go back to question number 2 first. And so a microcode slice is a location in ROM. So now the most important word is what I mean by implement. Okay, so the word implement in the context of the processor, and particularly in terms of the ROM, has a very specific meaning. In yesterday's lecture, when I used the word implement, it was used in the context of this particular location in ROM is specifying, okay, implementing what is needed to configure the processor to actually perform the function of this instruction. So that means location 000 and 001 are not part of the question. They're not part of the answer, because location 000 does one thing. Okay, it is corresponding to the fetch cycle when we execute instructions. Is it specific to the LD instruction? The answer is no. Okay, every single instruction needs to start with a fetch cycle, which is done by the microcode slice at location 000. Location 001, okay, does a different job, okay, but nonetheless, it is also being shared by all instructions. It doesn't matter what instruction you need to execute, location 001 gets one particular cycle done, and that has to do with the decode cycle. So location 001 in the ROM is corresponding to a slice that is generic to the execution of every single instruction, and that is called the decode cycle, and which we also talked about in yesterday's lecture. So what do we do after location 001? Okay, where does it go after location 001? So in yesterday's lecture, I was using the ST instruction as a demonstration, but the generalization from that discussion is whatever the opcode is. In this case, it is 7B, okay? So whatever the opcode is, it forms the most significant 2 digits of the location of the microcode slice that implements that particular instruction. In yesterday's lecture, I believe it was a F9 something. It was a F9. The opcode itself is F9 in hexadecimal. So we went to F90 to get to the first microcode slice to implement a specific store instruction. In today's, in this particular lab, we have a 7B. So 7B is okay, so Catherine is asking, is 7B the location or is it the content? That is a very good question. 7B in RAM is the content in RAM. Okay, so one particular byte as content, as value, okay, at a RAM location, the 7B, that specifies the opcode. So the opcode is in RAM, which means you can load a different program, you can load different instructions and different opcodes. But when that opcode is put into the instruction register and then in return put into the microcode pointer, or the microcode pointer, then it becomes the location. It becomes a location in the ROM corresponding to 7B0 in this case, and at the location 7B0 in the ROM is the slice is the slice that specifies all the zeros and ones to configure all the multiplexers, demultiplexers, registers, RAM, decoder, and whatnot in order to perform this particular specific operation, which is using register D to specify the location, and we get the value from that location in RAM and then store it into register C. So how would we figure out the answer? All right. So there are 2 ways to do it. The way I just did it was analytical. It was just interpreting. Okay, so first of all, the key is what the question is asking. The question is asking what is the address of the first microcode slice. So that would mean it is going to be, because it's in hexadecimal, so it is 7B0, not just 7B, because 7B is the opcode. That's what you put in RAM to specify that, oh, we need a load CD, operation. But that's what you want to do. It is not how it is done. The ROM contains all the bit patterns to specify how something is done. So that quote unquote how something is done is implementation. And at the location 7B0, which is right after the decode cycle, that slice in the ROM, that location in the ROM, has exactly the bit pattern that we need in order to configure all the components in the processor to actually implement or to actually use register D to specify the location in RAM, and then grab that content and put it into register C. So I'm not sure whether I'm answering the question or not. Are we good here or not? All right, so Catherine wrote, I originally figured it out by running the program in, you mean in the simulator, in Logisim? Yep, okay. Yeah, so you can do it that way too. That actually is a very good way to do it because it is reinforcing your understanding of the processor, because you're going to start with location 000, and you can observe that the fetch cycle is putting 7B into the instruction register. And then when you get to location 001, you can observe that 7B is, we attach the least significant 0 to it, and then we put it into the microcode pointer in location 001 of the ROM. And then we got to that specific location 7B0, and then we can see how the processor has all the correct configuration to perform the actual operation. So that is perfectly okay as another way to answer the question. Yep. Yes. the left side of the round box, is the address. So when you look at the round box here, so instead of just talking about it, why don't I just do it? Okay, so with this one, I can just inject a different instruction here. I think Catherine also, um, mentioned something that is kind of important, is when you want to run the program from the beginning again, you have to reset it. Now, when you reset, you can just do a global reset. In other words, you can go to simulate and reset simulation. That works with one little caveat. So this resets everything. Since it resets everything, that means all the content of RAM is gone too. So now we just have to go back into RAM and then put in the program. So in this case, we have 7B as our load instruction, and then the 0, 1 to halt. The 0, 1 is optional because since I'm going to use Control T to do it transition by transition, that means I'm not going to run it at full speed, which means the halt instruction is probably not needed. Okay, so that's okay. The 0, 1 is not needed. So now what we do is we repeat kind of yesterday's experiment, which is a good thing to do, okay? Because from your perspective, yesterday was the first time that we did all of this, so it's good to do it again and again. So Catherine's asking, what are the 0004 at left of RAM? Okay, so let's check out what is there. Oh, you mean over there? These are the addresses. So 00 is referring to the address of the 7B. 04 is referring to the address of this particular 00. 08 is referring to the address of this particular 00. So they are really a much more abbreviated format of the full edit content view. Because in the full edit content view like this one, each row has 16 bytes, and that's why you see in hexadecimal the address increments by 16, which is 10 in hexadecimal. But in the much smaller view, we only got 4 bytes in a row, and that's why you see the address only incrementing by 4 row by row. Okay, you're welcome. All right, so oh, right. So we are now, getting back to the lower portion of the processor because, that's where most of this is where everything starts. Okay. So if you want to understand how the processor works, this is where everything starts, is to look at the bit pattern that is being spit out at the D port of ROM, and that specifies what we need to do. This is the fetch cycle, and I'm not going to go through every single little bit of explanation of the fetch cycle because we talked about this yesterday. So it suffices to say that in the fetch cycle, the opcode that is currently pointed to by the program counter is put into the instruction register over here. So when we have a rising edge of the clock, we can expect the instruction register to get 7B. So I'm going to type Control T on the keyboard right now, like so, and we can see that's exactly what happens. Okay, the instruction register is now 7B. And when we do a falling edge, every single falling edge updates the microcode pointer. In this case, the microcode pointer is just going to increment because we are done with this particular slice of microcode. Now this is a slice of microcode. It is just not a specific microcode slice to implement a particular instruction. So we do a Control T, and we can see how the microcode pointer is has incremented to 1. So now it is the time for the second microcode slice, which is corresponding to the decode cycle. The decode cycle has nothing to do with, so the program counter will first increment, which is the first thing that we do in the decode cycle. It's kind of more of a side effect of the decode cycle. So when we do a Control T, we see the program counter is now a 0, 1 because the location 0, 0 is already quote unquote fetched. Okay, so there's no need for the program counter to continue to point to location 0, 0. But the falling edge is where things get a little bit interesting because the falling edge is going to take whatever content the instruction register has and use it as the most significant 4 to 11 bits. and use zeros to fill in the least significant 4 bits in order to update the microcode pointer. So upon this particular falling edge, the microcode pointer will change to 7B0. Okay, but remember, location 001 is needed in order to execute every single instruction. Okay, it is part of the instruction execution cycle, which then is common to every single instruction. It does not do a single thing about the load, the store, the add, the subtract, the compare, the jump. It really is just here and say, it's almost the same thing as, oh, let's flip a page. It has nothing to do with the content of the page or what the content of the page is telling us to do. It is simply a quote-unquote meta instruction to say, oh, let's go flip a page or look up a table to get to the page where the where the index is telling us to get to. Okay, so when I have a falling edge, so if I type Control T right now, we have a falling edge, and then the microcode pointer will update to 7B0, just like that. So when you get to the location 7B0, it is not the same for every single instruction. In fact, at this point, it is unique to every opcode. So every opcode has a unique location to decode into, so to speak. And when you look at the configuration of all the components of the processor, now it is ready to go to the location that register D is pointing to, and then grab the content at that location of RAM and store that into register C in the register bank. I'm not going to go through that process because this is very, very much alike, with the store instruction. It's just the opposite direction. Okay, so instead of storing something into RAM, we are now grabbing something from RAM, but it's just the reverse opposite. It's just the opposite direction compared to what we did yesterday with the store instruction. So I'm not going to go through every single how to analyze each component for this instruction at this point. So with that demonstrated, do we have any questions about question number 2 of this exam? Okay, so that's not what I intended to do. I was getting back to, oh, that's the correct one. So do we have any additional questions about number 2? Particularly about the concepts, okay, what I mean by a microcode slice, what I mean by implement, and how we get to the address and not just the content. Okay, I'm not seeing any questions, and Catherine is typing. The microcode slice is the location. So every slice is corresponding to a location in ROM. So it's corresponding to content, not the address. And that's why the question asked about the address of the first microcode slice. All right. Okay, so let's move on to question number 3. If you have a question about if you have something to say about an earlier question, do not hesitate. We can always go back a little bit if we need to. Okay, question number 3 says LD is a simple instruction. It is implemented again. Okay, it means that single slice of microcode configures the components inside the processor to perform the function that we want to perform with this instruction. So in question number 3, it asks, look up the ROM of the processor and find out what is the first slice of the microcode and blah, blah, blah. So it looks like it's asking the same question, but this time it is not asking about the address of the slice. It is asking about what is the first slice. In other words, it's asking you about the content of ROM in this case, and not the location of that content in ROM. So in this case, there's no easy way for me to answer this question without actually looking into the ROM component, because the hexadecimal digits corresponding to that location even though I designed this whole thing, but I have to go through a lot of, tedious process to basically recompute the 1503056. So at this point, it's just really copying the content, which is what is highlighted in ROM, into the answer space. So I'm pulling this off because I can't see both at the same time. So it's 1503056. So one is corresponding to the address, and the other one is corresponding to the content at that particular address in ROM. Because the ROM has to be wide. Okay, so the question is, why do we have 7 digits in ROM but not in RAM? Because the data port of ROM has to be wide enough to specify all of these tunnels, and it took me 26 bits in order to specify all the things that I need to configure all the components of the processor to do what needs to be done. So that's why. So if you divide 26 by 4, okay, and take the ceiling of that result, so 26 divided by 4 is 6 point something, right? And you have to take the ceiling, which means your 6 point something, as long as that something is non-zero, would round quote unquote up to 7. And that's why we have 7 digits, because we need 7 digits to express 26 bits. So that's a good question, but it has to do with the width of the data port that we need in order to configure all the components inside the processor. So are we good with that? All right. So I'm gonna move ahead to question number 4. So question number 4, it says, the ST instruction has the mnemonic syntax of STYX. The reason why X and Y are reversed in this case is because, I want the first operand to specify what is changed by the instruction, and the other one is, basically just specifying, the supplier of the data. And then the first operand, which is in parentheses Y this time, specifies who is the consumer of that data. So in this case, the value of X is copied. Oh, okay, bad grammar over there. So the value of register X is copied to the RAM location pointed to by register Y. Again, X is one of the 4 registers, and so is Y. How many variants are there to this ST instruction? In other words, how many ways can we combine the registers for X and Y? And remember, we can use the same register for both X and Y. So the answer is 4 times 4, which is 16. 4 choices for Y, 4 choices for X, and for every single value of Y, we have 4 choices for X. So that's why we end up with 4 times 4, which is 16 possible ways. Are we okay so far up to question number 4? All right. No comments, no feedback. Okay. All right. So we move on to question number 5, which is starting to introduce the concept of a label. So the assembler, okay, I'm just reading the text here. The assembler accepts label definitions. This is a handy feature because otherwise the programmer would need to count the number of bytes used in code. A label definition is an identifier and uses the same rules as a C variable name. And by the way, a C name, as a variable or as a function name is called an identifier as well. And the definition is followed immediately by a colon. So there's a colon right here after the L2. A label definition must be the first thing of a line, so you cannot have an opcode or a mnemonic first, and there should be nothing other than comments after a label definition, which is a lie, okay? And later on we'll see why that is a lie. But for now, okay, let's just say that that applies, okay? You can only have a label and then a colon and then just comments, okay? Nothing else after that. For example, the following line defines the label L1 with a colon. Note that a label is a symbolic name of the address of the following byte. In other words, in the following code, L2 is a symbolic name of the address of the first byte of the LDI instruction, because the LDI instruction has 2 bytes. So the label L2 is corresponding to the first byte of the LDI instruction. Assuming the above code is at the beginning of a program. In other words, the first opcode is at location 0. What is the value represented by label L2? So that's what the question is asking. If you interpret, okay, now I can never really quite I cannot assess, okay, whether the description here is sufficient or not. So if you guys think that it's not sufficient, you have to let me know, why it is not sufficient. Okay, what is missing from the description here to describe what the label is in order to answer the question. So assuming the above code is at the beginning of a program, the LD instruction takes up 1 byte, and then the label is the symbolic name of the byte that is after it, which is the first byte of the LDI instruction. Now, do we need to know the LDI instruction takes up 2 bytes? That's actually not needed, because as long as it is after the L2 label, and as long as we know the LD instruction only takes up 1 byte, which we do from the first question, then we know the label L2 is really representing the value of 1. All right, so we got a question. The symbolic name is corresponding to a number. Look at it as a const definition in C or C++. So it's almost like const int or const unsigned x equals to a particular value. It is the symbolic name of a specific value. In fact, I can show you in the assembler how it is represented. So I'm going to wait until Richard is done typing. And so Richard is typing, why isn't the value of L1 an address? It is. It is. So the value of L1 is actually an address. But we don't want to use the concept of an address unless it is necessary. Because L1, as far as the assembler is concerned, it really is just a number. Okay, so let's go to the assembler and type in that program. And this also prompts me to answer one of the questions that someone has in class, or somebody encountered this problem, is even though it's okay to type code inside the source tab, it's perfectly okay to do this. So I can just type ldcd L2 and then LDI instruction. I cannot remember exactly what it was, but I'm just gonna type some here. So it's perfectly okay to type your program like this. However, what you do not want to do, absolutely do not want to do, is to click on one and then you say delete cells or delete row or delete column. Do not do any one of those operations, nor inserting. So that means you can only change the content of a cell that belongs to column A inside the source tab, and do not touch anything else in any other way. Okay, so do not try to remove cells, because that's going to shift the references the rest of the spreadsheet relies on. So the best way to putting the program into the source tab is really editing the program using a regular text editor. Notepad is fine. If you use Vim, that's fine. Use any text editing program to edit the program first, and then copy and paste it into column A. That would be the safest way to utilize the assembler. Doing in-place editing, just like what I did, is okay, but you have to be careful. Okay, so if you need an additional line between, say, line 1 and line 2, and usually what we want to do, for people who know how to use a spreadsheet, which is most people, you can click on this and say insert a row above. Don't do that, because if you do that, you're going to break the assembler. The assembler is not designed to handle editing inside the spreadsheet. So just copy and paste into the spreadsheet from outside. All right. So the idea of this demonstration is to show you where you can get insights into the program. This is obviously just the beginning, because we'll get to do this quite a lot more in the future. So the first one, excuse me, that is kind of interesting is the assemble tab, which we had used already. Okay, so when you look into the assemble tab, I don't know why it has these widths. I think I specifically use those widths because they can be wider. So particularly what we want to do is to look into, so I'm shifting the columns to where I need to show you. So if you look at column U and column V and column W, column V is basically the addresses but in decimal, and then column W are the addresses in hexadecimal. So we know this part already because of one of the earlier labs. So we know column W are the addresses corresponding to a row. Column U is corresponding to label definitions. So we can see that label L2 is corresponding to address 1, because at that particular moment of time, the assembler is basically saying, okay, whatever is next is going to have location 1. Why? Because the first instruction, which is the LD instruction, has used up location 0 already. So that's basically how the definitions are done. Okay, so if you use a label definition without anything after the colon, it would just say, okay, I'm guessing that you just want the quote-unquote current location in the process of assembling a program. And that's why L2 gets a value of 1. So the other thing you can also do is to go to the sim tab sim tab. Okay, so sim tab is not symbol tab, it is symbol table. So that's why sim tab is the official name of this particular tab in the spreadsheet. So when you go to this particular tab, A1 as a cell is the symbol table. It shows us the L2, okay, which is from line number 1 because we count from 0. It has no unresolved references to other labels. And then RPN stands for reversed Polish notation, which we'll get to later, okay? But for now, if RPN is in square bracket just a particular integer, that is the definition. That is the value that the label is defined to. Now, what about the other stuff? What is the address? The address has to do with, in the assembling process, the definition of L2 is encountered when the assembler address is 1. And there are no errors associated with this particular symbol definition, so that's why you see an empty string corresponding to error. This notation here is known as JSON, JSON without the A, which is JavaScript Object Notation. You don't need to know this, okay? I'm not going to ask any questions related to this, but for those of you who want to understand more about how the assembler works, because that can be helpful to debug your program. That's basically what it is. The other two values are not really useful as far as your program is concerned. This is really just reflecting how many lines are actually used in the program, and there are 3 lines to this particular program. And I'm not really even sure what this one is about. This one is, oh, this one is basically answering how many opcodes in mnemonics we have with this particular processor architecture. They're not all opcodes. Some are not really exactly opcodes, but there are 31 quote-unquote instructions that the assembler recognizes. So that's what the 31 is. So these two numbers you don't really need to know, when you are just using the assembler as a tool. Okay, I need to use these values because I'm implementing the assembler. All right. So I just talked about a little bit more than what I need to. There we go. All right. So that's the answer of question number 5. So getting back to the lab, are there any questions? So I think I just answered Richard's question. The value of L1 can be used as anything. So in this particular case, anytime you want to refer to the number of 1, you could use L2, okay? But if you insert any code in front of L2, then the definition of L2 will change. But other than that, okay, if you just need to refer to 1, L2 is basically the same thing as the constant 1 in this particular code. All right. So without any questions, we're going to move on to number 6. All right, number 6 is, okay, so I'll just read the text first. Labels can be used as an immediate value. This means LDI, the LDI instruction can use a label as the I part. So the I part refers to the opcode table. So when you go to the opcode table and look up LDI, which is here. So the LDI instruction, has two components. X is one of the 4 registers, and then I is what we call an immediate constant or an immediate value. When you look at this column C, which is describing what it does, it's really kind of awkward. So there are 2 ways to look at this, okay, or 3 ways to look at this. The first way is x equals to star dereference PC++ in parentheses. Or you can look at that as x equals to RAM, and this time we are looking at the content of RAM as an array in square brackets PC++. Or you can simply look at it as the comment is star PC equals to I, which means the program counter by the time we get to the microcode slice that implements the LDI instruction, the program counter is pointing to the immediate constant. So this is one thing that we can show. Why it is PC++? Very good question. So this is what we'll do next. Okay, we're going to play with the LDI instruction in the simulator, and by going through that process really step by step, transition by transition, we'll see why it is PC++, okay, and why the plus plus is really, really important in this case. So getting back to the question, I'll answer the question first, and then we'll do something in the simulator to illustrate this instruction. So when the program gets to the halt instruction, what is the value of register B? Specify the answer as an 8-bit binary number. Okay, so with this one, you can do it in, let's see, 2 ways, okay? Mostly 2 ways, but you can also have a kind of a 1.5 way, which is somewhere between 1 and 2, okay? So the first way is completely do this analytically, okay? Which is, I think I understand what the LDI instruction does. I think I know what the LD instruction does, and so on. So if you try to do it that way, then you know that L1 is the address of the first byte of the ST instruction. So that address is being loaded into register A in the LDI instruction. In the second instruction, we are using register A as an address, as a pointer. We go to that location in RAM, grab whatever is the content at that location in RAM, and then put it into register B, and then we have a halt instruction. So in that case, if I can use the opcode table to hand assemble the ST instruction, which is not too hard, right? Because we did it yesterday too. So let me use where's my little post-it tool? There we go. All right, so I'm going to put my post-it tool here because I need a little bit of space to work this out. So the STAD instruction is what I need to hand assemble. We get to the opcode table, we look up the ST instruction, which I think is down here, that's right. And go back to my notepad. And I'm going to make this one always on top, so this way, it's, I don't have to kind of go back and forth. All right, so the ST instruction starts with 1111. Register X in this case is register D, which is 11, and then register Y in this case is register A, which is 00. So in hexadecimal, this is a FC. Okay, so let me see. It's a 0xFC, which means it is in hexadecimal. It is FC. So that means, okay, if I go back to the question here, so that means the other way to specify this content here is really just to say, oh, we just need to stick a byte, okay, that has a hexadecimal representation of FC. It would have done exactly the same thing. because I just hand assembled the program. Oh, can't see the clock. Oh, because of the clock. Okay, gotcha. Let me move this one above the clock. There we go. Yes. You mean the hand assembling? Because Catherine asked, could I do that again quickly? So are you referring to the hand assembling of the opcode? Oh, okay. All right. So so once again, the opcode is done by looking up the opcode table. We know that the most significant four ones are, they need to be there, they're constants. And then the XX refers to the second register this time, which is register D, if I remember correctly. Yeah, so that's register D, and that's why we have the 1 1 in this place. And then the register Y is register A, which is represented by 2 bits, 0 0 over here. So when you look at 1111, that is in hexadecimal F, and then when you look at 1100, which is 12, it is hexadecimal digit C over here. All right. So we know this byte has the content of FC in hexadecimal, but we want the answer to be in binary because everything is, when we mention bits, okay, which is binary digit, it is implicitly it is a binary number, but it also spells out as a binary number here. So we have 1111 1100 in this case. So this is how I can answer the question in method number 1. Method number 2 is just copy and paste this code into the assembler, download the RAM file, and then actually just run it in the simulator. When the simulator gets to the halt instruction, then we stop the simulator, we go into the register bank, we look at what is in register B, and then copy the answer over here. So that's method 2. So what the hell is method 1.5, which is between method 1 and method 2? June is typing something. I'm gonna wait until we get that. So I'm gonna copy and paste this code. All right, so June said, what is the value of L1 in this case? So that is a little bit more troublesome because now you need to know how many bytes each instruction takes. The LDI instruction takes up 2 bytes, so that would take up location 0, 1. This takes up location 2. This takes up location 3. So by the time we get here, L1 should be 4. And Catherine is asking, is it PC++ because LDI takes up 2 bytes? And that is correct, because if we do not do a plus, then we'll treat the second byte as the opcode in the next fetch cycle, which usually is not a good thing, because that's just a constant that we need to load into a particular register. It probably is not intended as an opcode. So that's why we need the plus. So Catherine is correct about that. But let me get back to answering question number 6 in using method 1.5. So we get to the assembler, we get to the source tab. Okay. And it's perfectly okay to paste something into column A, and as long as you don't double click and see the blinky cursor first. Okay, so if you see the blinky cursor, just press the escape key or press the enter key, or click on some other cell until you don't see the blinky cursor. Then you can do a Control V, paste the program in. So this is method 1.5, which is somewhere between completely just analytically looking at the program and figuring out everything on paper versus running the code and look at the actual end result in the simulator. So this method basically is in between because we use the assembler to tell us what is at location 4, and that is the answer. So we are kind of, we are saving the step of hand assembling the store instruction, and but we are still using our understanding of the concepts to answer the question and not actually running it through the simulator to answer the question. But we can also see, how the LDI instruction is taking up 2 bytes, 6C and 04 respectively. The LD instruction is only taking up 1 byte. The hold instruction is taking up 1 byte. So if you do the counting, by the time we get to the ST instruction, it is at location 4, and because the L1 label definition is basically the symbolic name is the address of whatever is following it, that means it is also defined to be 4. All right, so Catherine has been typing for a while. I'm going to wait for, oh, there we go. You could also run it in the simulator and look at the register. Yes, so, all right, so let's go ahead and do it that way too. Okay, so we'll try to answer this question in all 3 different ways. So the method 2 involves going to the RAM file. So don't forget, okay, if you want to load something into RAM, you have to make sure the RAM file is the selected tab before you go to File and Download. Okay, this is really important because I think some people try to use something else to do this, and try to use another tab to download the program, and that does not work. You have to be on the RAM file tab to do this. So now we save the file. I'll just put it into my temp folder, call this example 1. Okay, there we go, example 1. There we go. And then we switch back to the simulator, and I'm going to move my notes off screen because we don't need it right now. And since I'm going to rerun the program, I have to restart the processor. So Control R is another way to reset the simulator. Okay, so type Control R and everything, including RAM, is now reset. So RAM is basically all zeros again. Right click, go to Load Image, specify the path. It's already in the right folder, so I'm going to just type in the name of the file, which is example1.csv. And now we decode in. So what we'll do now, okay, is going to serve 2 purposes. What I'm going to do now is both answering question number 6, but also to illustrate how the LDI instruction works. Okay, in a blow-by-blow, transition manner. Almost. I said almost because I'm just gonna zip through the first 2 cycles, the fetch cycle and also the decode cycle. So Control T, Control T, Control T, Control T. So now we get to the microcode slice that implements the LDI instruction, this specific LDI instruction. So we want to look at this slice and ask, how does it get the job done? Okay, so we're going to go through the analysis that we went through yesterday. And you can do this to any instruction that you encounter, okay? And I highly recommend that you guys do it too, because even if you know exactly how the LD instruction works, for instance, it's still good to go through this process because it helps you locate the components faster when you need to do this again for some instruction that is more difficult to understand. So we'll start with RAM, and again, you might want to keep a list of the components to go through, so this way you're not going to miss anything, and it's a systematic way to get things done. So just go through, I just start with RAM, and we can see the RAM cell is a 1, which means that the RAM component is being used in this particular slice of microcode. And as soon as I know RAM is being used, I ask the second question right away is, are we reading from RAM or are we writing to RAM? And that question is answered by the LD port. If it is a 1, we are reading from RAM. So then I also automatically ask the other 2 questions. Who is driving the A port? Who's specifying the address? And who is utilizing the D port? Who is using the output, in this case, from the RAM component? So one thing at a time, I normally track down the A port first. So I looked at the A port. It goes into it's coming from a multiplexer. The select of the multiplexer says 1, so we look at input 1. We track down input 1 and ask, all right, so who is driving this particular wire? So it connects to two different points, this point and this point here. But this particular point is an input. It doesn't really specify anything on the wire or on the node. So it has to be coming from the program counter. So the program counter, which is now 0, 1, is telling the RAM to go to that location. And because it's a read operation, we are now effectively reading location 0, 1. But what exactly is at location 0, 1? Location 0, 1 is labeled L1. Okay, so 0, 4, which is what L1 is defined to, is actually using a byte in memory to specify it. And the program counter is pointing to this location because we have an auto increment of program counter in the decode cycle. So that's why we are now at this location. What are we doing with the content at this location? That question can be answered by tracking down the node that connects to the D port of RAM. So it connects to a whole bunch of stuff, okay? But because we know that the D port is driven by RAM this time, so we know we can ignore everything that can also drive this particular node. So we can ignore this particular demultiplexer, also partially because we know it is not enabled, okay? But everything that can take it in, we kind of have to take a look. So it goes into this multiplexer, which then goes into the register bank. So this one is important this time because we can see how the register bank has input enabled being a 1. And when input enable is a 1 with the register bank, we know that we have the intention to update one of the registers. So now we right click, go into the register bank and ask, all right, so what are we doing here? So this is the 4 that is coming from RAM, and the decoder is enabled, and that's why we see that's because of the 1 over here. And the most important part is which register are we updating? Register input select is 0, 0, and that's why we see output 0 of the decoder being a 1 and everything else being zeros. So that means register A now has the enabled being a 1, which means in the next rising edge of the clock, register A is going to be updated. It's updated by whatever is presented to the D port of register A, which is the 0, 4 that we saw. So this is how we can figure out that, oh, so we are using the program counter to point to a location in RAM, and then we take the content at that location in RAM and use it to update a register in the register bank, right? So that's detective work to figure out, what is being done by the configuration of the components in the processor. Why are we using the program counter? Because the program counter is now pointing to, conveniently, it is now pointing to the byte right next to the opcode, and that's where we stash the constant that we want to load into the register. So this is a fairly typical way to implement a load immediate instruction, and basically most processors that I know of would do it this way, with a few exceptions, with few exceptions to this particular rule. The immediate itself is not in the PC, it's not in the program counter, it is at the location that the program counter is pointing to after we decode the opcode. So the immediate constant is not in the program counter, and it is at the location that the program counter is pointing to right after the decode cycle. So that brings us to another question, right? Because when you look at the program counter, it also has its own enable turned on. So not only are we using the program counter to specify the A port of RAM so that we know where to look for that byte to update a register in the register bank, the program counter itself is also going to be updated in the next rising edge. So now we have to ask the question. So whenever you know a register is going to be updated, the next natural question is to ask, how is it going to be updated? So you have to you can do that by tracking down what is connected to the D port. So it's coming from a multiplexer. The multiplexer is determined by its select bit, which is a 0 in this case. So that means input 0 is being used in this case. So input 0 of this multiplexer comes from the adder, and the adder is definitely adding in this case because address mux is a 1, it goes through an OR gate, so the output of the OR gate becomes the carry input of the adder. So if the input of the adder is 1, then the output of the adder is going to be 2. So that 2 is going through the multiplexer and back into the program counter. So we know the program counter is going to be incremented to 2. The reason why, so this explains why it is a PC++, because we utilize the program counter as a pointer first to grab whatever is in RAM at that location. That is the PC. The post increment is what we are doing right now. What I'm trying to explain right now is, oh, by the way, okay, also add 1 to the program counter. But the reason why we're adding 1 to the program counter is the program counter is supposed to point to the next opcode for the fetch cycle. But what it is doing right now, 01, location 01, is not an opcode. Okay, it is a constant that is useful to the current opcode, but itself is not an opcode, or at least it's not intended as an opcode. We are not supposed to execute opcode 04 after the LDI instruction. So we have to increment again to skip this byte because it is now just used in order to specify the constant to put into register A in this particular instruction. So we have to auto increment the program counter also in order to get this done. So I know somebody's going to have this question, okay, because it's just natural and logical to ask this question. So the question is, but isn't this kind of like, pulling the rug under ourselves, because we are using the program counter to specify the content in RAM to update register A inside the register bank, but we are also going to change the pointer itself at the same moment. Isn't that going to be a problem? So what do you guys think? What do you think? Would this be a problem? And if it is, or if it is not, why do you think it is or it is not a problem? So we got Richard and Catherine typing. Maybe not, because the adder has to wait. And Catherine says no, because there's a delay. And you are both correct. But most importantly, it has to do with both transitions occur at exactly the same time when we have the clock transition from 0 to 1. So as long as there's no skew when the clock is transitioning from 0 to 1, in other words, as long as the program counter and register A in the register bank, they see the transition from 0 to 1 of the clock at really exactly the same time, we don't have a problem, because it takes a delay, it takes propagational delay in order for the program counter, once it is changed, to go through the multiplexer, and RAM is really slow. Okay, it's because when the multiplexer changes its output, which is here, then it takes the RAM to respond to that change of the A port, and guess what? That is actually a very long amount of time. Okay, so I'm going to sidetrack a little bit. I'm looking at the time is 10:05, so I'm going to sidetrack a little bit here, because when we look at the simulator, we don't really get a sense of how slow RAM really is. Okay, so the way we used RAM in all of our examples seems to suggest that as soon as we change the A port, the D port changes accordingly. Okay, if we change the address, the RAM will automatically and instantaneously go to a different location and use the content at the new location to output at the D port. That there doesn't seem to be any delay. That is actually not true. Okay, and then some people may suspect and say, well, maybe it operates kind of like maybe the adder, right? We got about 4 propagational delay between the changes of the input. to the sum being correct. Okay, I would say that's 5 propagational delays, which is not really a whole lot of time because we are only talking about 5 propagational delays of multiple nanoseconds each at the in the worst case. So it's not really a whole lot of time. RAM is much slower than that. Okay, every time you update the A port, it takes a long time for the D port to change accordingly. Okay, so how long are we talking about? In a real processor, if we are talking about using static RAM, which most processors don't use static RAM anymore, we use dynamic RAM in most modern architectures. But let's just say that we're using static RAM. It takes multiple clock cycles to change the D output from a change of the A input of RAM. In other words, not only do we not have to worry about, oh, we are changing the program counter and at the same time using what the program counter is pointing to update another register, not only do we have to not worry about the situation where we are quote unquote pulling the rug under ourselves, we actually have to allow additional clock cycles for the RAM to update its D output when we change the A output. Those are called wait states, or WS in abbreviation. So the wait states, which some of you will encounter because if you become a computer engineer or an electrical engineer, you have to account for actual delays in all the components inside the processor. So you actually have to program a processor to introduce additional wait states in order for RAM to do its job because it is a very, very slow device. Okay, so the answer to my earlier question is no, we have nothing to worry about in this case. Even though we are updating the program counter and also updating another register based on what the program counter is pointing to, it takes such a long delay for the program counter. It takes such a long delay between the time that the address port changes to the time that the D port changes accordingly that this is really a non-issue. In fact, it is a problem because the processor, when you look at all the components inside the processor, the RAM is not really a component inside the processor. It really is in the diagram, but it's not really inside the chip itself. And in some of the integrated chips, it is inside on the same die, but it is typically looked at, as a quote-unquote separate component, even though it may be on the same physical die as the processor itself. So the issue is RAM is so slow, okay, and the rest of the processor, even the ALU, okay, which has to do all the adding, subtracting, and whatnot, those are really, really fast by comparison. So that's why we have a bottleneck. Okay, the bottleneck of earlier processors has to do with how quickly can we get something out of RAM. Because RAM not only does it contain the data that we need to process, but it also contains the instructions that will tell us what to do next. So we have to keep waiting and waiting and waiting for RAM to respond to changes to the address port. And that becomes a problem because when silicon gets smaller and smaller, or when transistors get smaller and smaller, the processor itself, the registers, the ALU, the adder, the subtractor, and whatnot, they can all get their job really fast. But by comparison, RAM is always still way slower compared to what the processor really can do. And that's why we have caching in modern processors. It's not really just modern processors. Caching is a concept that we use as early as the Intel 386 processors when we are only talking about personal computers. So that's what cache is for. Okay, now this is obviously a sidetrack compared to what we are talking about here, but I think it is still useful. Okay, it's still useful information for most of you. So caching is basically having a inside the processor. Okay, basically cache is a component. Okay, if I want to draw a picture, let me see if I can do that. Doesn't look like it allows me to draw some picture around here. So if I were to put a cache component, it will be about here. It is a shortcut. Okay, it's a very localized stored copy of certain locations of RAM. So if you use a certain location in RAM repeatedly, then the first time it will take a long time because you really have to get to RAM to get the content. But then it becomes quote unquote cached inside the cache component. So the cache component is a very fast lookup mechanism. If you say, oh, by the way, I want to get to location 01 again, the cache will first look up its own internal space and go like, well, did we access that location very recently? Yes, we did. Oh, great. It has a content of 04. So the cache can return the content at a location really fast if it was used very recently. On the other hand, the cache doesn't have the same capacity as RAM. So in the scale, okay, for those of you who build your own computer or you purchase computers and you want to look at all the specifications, you can see that even with the latest and greatest Intel i7 processors or even i9 processors, the amount of cache is still measured in maybe double-digit megabytes. Okay, that's a lot. That's huge compared to a consumer grade processor, which typically has a single-digit megabyte of capacity as far as the cache is concerned. But when you compare that cache amount compared to, if you compare that to how much RAM the same processor can address, so I would say that an i9 processor probably has an address space of 64 gigabytes or more, maybe 128 gigabytes. So when you look at maybe 12 or 16 megabytes and you compare that to 128 gigabytes, it's off by a lot. Okay, so the amount of cache compared to the amount of memory is really it's a huge ratio in this case. And this is also why, when you write an algorithm or when you write programs or when a compiler compiles a program, locality becomes a key issue. Because if you can keep a lot of code that you need to run within a very small contiguous space in the program space, then caching works very effectively because you're reusing the same chunk of memory repeatedly all the time. On the other hand, if your execution pattern is all over the place, then caching doesn't help much because by the time you get back to the first instruction that you started off with, the cache is already thrown out because it has not been used for a while. So that's kind of something that you can keep in mind when you get into optimization topics in some of your other classes. I'm digressing a little bit here from the context of our class, but it is related because because I just needed to answer the question of are we pulling the rug under ourselves? The answer is not really, because it takes so much time for the rug to move, so the act of pulling it doesn't really change the rug itself at all. So are we good so far? So Catherine is absolutely correct. Not only is there a delay, it is a huge delay, because RAM takes so much time to change the output based on its input. All right, so if there are no questions, we're going to move on. So question number 6, and I think question number 7 is the last one. So the question number 7 says there's a by the way, byte itself is not called an instruction, it is called a directive. Okay, so a directive is basically just an instruction to the assembler, and just say, hey, just allocate a byte and initialize that byte to the binary bit pattern of 84 in this case, and then a 97, and then 107, and so on. So let's see what happens when we put this into the program. So I'm going to put in this code here. Okay, so copy and paste it. So here's copy, go to the assembler, go to the source tab, and paste. All right. So this time when we go to the assemble tab, it's kind of like, oh wow, not really surprising. Well, okay, so there are some things that are a little bit kind of interesting, but most of these are not interesting at all. So you can see on row 4, when we say byte 1, it really just specifies a byte at that location, which is location 03. At row 3, we specify 117, and 75 turns out to be the hexadecimal representation of 117. Location 1, kind of the same deal, 109 in decimal is represented by 6D in hexadecimal. What is a little bit more interesting is row 2, which is byte L1. So byte L1 is telling the assembler to 1, allocate a byte, 2 is to initialize that byte to whatever the expression is after the after byte itself. So in this case, what is after byte is L1 as a label reference, and the label is defined on row 5, and we can see how the label is defined as 4, because by the time we encounter the label definition, the assembler's address is incremented to 4 at that point. So that's why L1 is defined basically to 4, which also means every single time we see L1, it is the same as seeing 4 as a numerical value. So that explains row 2, why we allocated a byte at location 01, and also why that particular location is initialized to 04. Then we move on to row 6. Row 6 looks really kind of awkward, especially if you just look at the source of it, because we are at location, quote unquote, at location L1, and we're defining a byte to be just L1. Well, I don't see a problem, because if we know what L1 is, okay, L1 is just a label, which is a symbolic name of a number, of a numerical value. In this case, the numerical value is the address of whatever byte that is after the definition of the label, which is 4. Which also means to the assembler, seeing L1 is basically the same thing as seeing 4. Every time it sees L1, it will look up the symbol table and will say, what is the definition of L1? It's 4. So when we look at row 6, which is basically just a label reference to L1, well, guess what? It is just 4. So this time at location 04, we have a content of 04 as well. So when you look at this code, okay, and if you want to find out what it does, okay, you can just run it. But I can run this without using the simulator, okay, and to a certain degree, you guys can do the same thing too, okay, but it takes a little bit of getting used to. So let's go ahead and try to run this code without using the simulator. So to do that, I need a little bit of help here, because I need to track quite a few things. The first thing I need to do is to look at 6D and ask the question of what is the mnemonic corresponding to that. Mnemonic corresponding to 6D. So to answer the question, we go back to the opcode table, and then we look up column A, and then we ask which instruction would fit the bit pattern of 6D. 6 is a 0, 1, 1, 0, and then the D is a 1, 1, 0, 1. So we look at all of this pattern here, and we can find that 6D is all of these are 6. David is asking, oh, okay, the clock is blocking my little post-it here. Thank you. There we go. So we can see that these are all 6 something, right? Because 0, 1, 1, 0 is a 6, but they are not 6Ds, okay? 6D can be this guy over here, because 6D is 0, 1, 1, 0, which is the 6, and then the D is 1, 1, 0, 1. So row 22 corresponds to, it will match that particular pattern. So we know that 6D is corresponding to LDI instruction. So now it's time to figure out, but which register is corresponding to X as a placeholder? Because it is a 0, 1 that is taking the bits of XX, and 0, 1 is corresponding to register B. So that means, when we look at the mnemonic, it is a B over here. Then what about the I? The I is not a part of the opcode that we see here. The I is the byte that is right after that, okay? So when we go back to the source code, which is in the assembler. Okay, so when we look at this 04, it really is the immediate constant of the opcode. So the first instruction is really LDI B and then a 4. So this is corresponding to the byte 109, 109, and also the byte L1. Okay. The next instruction is corresponding to the bit pattern of 75. So now we have to look at 75 as in hexadecimal, and then we ask what is the mnemonic corresponding to it. So once again, we look up the opcode table, and this time we're looking at 0111 as the most significant 4 bits. Ah, how convenient. The next one is exactly the pattern that we need. So we now know this is corresponding to LD instruction. So now we need to figure out what is XX and what is YY. 75, the 5 in 75 is a 0101. Okay, so this time we're using the same register for X and Y, and they are both register B because 01 is corresponding to register B when we want to select one of the 4 registers. So we have an LDBB in this case. And then we go back to the assembler. What is next? What is next is just a 01, which we know is the halt instruction. Or if you prefer to really confirm and look it up, you can just look up the halt instruction, which is here. And that really is just 01 in hexadecimal. So now we have a halt instruction. Then we have L1 as a label definition, and at that location we have a byte 4, which is just a 4. So after I clean this up, okay, we're doing an LDIB4, we do an LDBB, we do a halt instruction, and then at location 4, which is L1, so you can always change this 4 to L1 if that is more readable. So at location L1, we really just have byte L1 or byte 4. They're the same thing. This is our program. So we are putting L1, which is 4, into register B, and that's the job of the LDI instruction. And then in the next instruction, we are using B to specify where should I go in RAM, and that's location 4. Grab the content at that location and put it into the same register B. Well, location 4 has a content of 4. So it really doesn't change register B because register B continues to have a bit pattern of 04. But it really is, it's updated twice. It's just that the second update is putting the same value into the same register. So using this method, I can now answer the question. And what is the value in register B? You may assume this code starts at location 0. Specify your answer as a base 10 integer. It's base 10, it's base 16, 4 is the same whether it's base 10 or base 16, so 4 is the answer in this case. And I think that's the last question. Yep. So this is how I can answer this question without actually running it, because this really is just another way to specify the opcodes without using the mnemonics. The idea of using the mnemonics is it's just easier for us to read as humans. But for someone who says but I want to go through the trouble to hand assemble every single opcode, well, knock yourself out. Okay, there's nothing saying that you cannot do that. It's just very inconvenient when the program gets larger. All right, so that answers all the questions, and if I submit, I'm hoping that I will get a perfect score. But sometimes I make mistakes. Not sometimes. A lot of times. All right, so far so good. All right. So are there any questions before I stop the live stream? Because the idea of today's lecture is really try to interactively answer all the questions concerning the labs from yesterday, particularly concepts, questions, questions related to concepts of what we have talked about so far. Okay. All right, so I'm not going to give you guys a new lab today, because we kind of need to talk about more concepts before we move on to the next lab. But I do want to give you a preview of what instructions will be. Well, it just means that we got more things to do later, right? But I do want to give you a preview of what instructions is in the next lab, because what you can do is to use the simulator to try to do a clock by clock, transition by transition uh, play with with those instructions. So the next few instructions we'll be talking about, I'm just moving to the lab. This is the next lab, okay? I'm not assigning it today, so don't worry that you cannot work on it today. So we have the increment instruction. So I'm just going to write it down on the side here. Okay, so this way it's actually in the display. So there's the increment instruction. And I think there's some branch instructions. So there's JMPI as a branch instruction. There's CMP as a compare instruction. JCI, which is a very interesting one because it's conditional branch. This is how we will end up actually doing conditional statements. This is how we implement conditional statements in C and C++. And this is the program that we'll be kind of playing with in tomorrow's lab. So I'm just going to go through this code here to make sure that I have a list of instructions that will be additional instructions. The JXI is not a real instruction. It is supposed to be replaced by a few other instructions, so don't worry about that one. So I think I got this list done here correctly. So instead of using your time to do a lab today, you can use the time to review today's lecture, and also to play with these instructions. They are all documented in the opcode table, so you can try to interpret their descriptions in the opcode table, and I believe they might be in the assembler manual as well. I'm not 100% sure. Even though I wrote it, I cannot remember what I wrote some time ago. So look into these instructions. Just write very, very simple programs, okay? Like a single increment instruction, okay? And then just single clock through it to find out what it does. A single compare instruction, but then you have to kind of inject values into the registers before they compare. And JMPI and JCI, they are a little bit harder to play with because they are branch instructions, which means you probably want to have a program that has at least 2 or 3 instructions in order to see the effects of the JMPI or the JCI instructions. But increment and compare are relatively easy to experiment. And the more you go through the process of kind of following what I did today, assemble a program, put it into RAM, and then single clock through the whole thing, and then examine how the processor is configured in order to implement a particular opcode. That is going to be helpful because that's basically studying for this class at this point. Is really just to go through the simulator and try to convince yourself that you understand. Well, okay, not to try to convince yourself, but to use the simulator as a tool to understand how the processor works. Okay. Catherine is asking, how do we inject a value into a register? It's just clicking on it and then changing it. So if I want to go to the register bank and inject a value into register A, you first have to make sure that you're using the poke tool instead of the selection tool. So use the poke tool to select whatever register you want to change the content of. Make sure there's a red rectangle around the value displayed by the register, and then just type on the keyboard. If I want register A to have a new value of 5D in hexadecimal, just type 5D, and that becomes the value of the register. So this is how you can inject values into a register before you start to run the program. So the process is to reset the processor first, load the program into RAM, inject values into the registers, then you can use Control T to examine what the processor does, transition by transition. All right. So Are we doing okay? All right. So I will still be online, after taking a 10-minute break, and then I'll be back to answer questions, because it is lab time. I'm supposed to be, with you guys, during the lab time. So if you guys go through, maybe some of these experiments and you have questions, come back to Discord and I will try to address your questions. So I'm gonna stop the live stream now. Oh, okay. I'm gonna wait until Catherine is done typing. Oh, thank you. You're welcome. Most welcome. All right. So I'm gonna get out of live stream at this point, but I'll be back in 10 minutes. It is 10:31, so I'll be back at, let's say, 10:42.